Hello, I'm Mr. Rose, and today we're going to be talking about work done by a variable force, in particular work done by a spring. Now, the reason why we talk about work done by a spring is a good non-constant force that is a very good approximation for nature. Some small vocabulary: a relaxed state is when a spring is neither compressed or stretched, just in its relaxed equilibrium position. A restoring force, as you can see from my picture down here. If I have a spring in a relaxed or an equilibrium state and I start pulling to one direction, the restoring force is the force that's trying to bring it back to that equilibrium position, which is defined here by Hooke's law. Fs is the spring force, is negative kx. That negative is showing that the force is in the opposite direction of my pull. So I'm doing work on this object. The restoring force, or the spring force, is coming back in the opposite direction. So here's a quick example to get us on the right page. If you have a 20-kilogram block attached to a real rope, now that real rope means the rope can stretch. It has some elasticity to it. We're saying that it's attached to a 500-kilogram plow. We're saying the plow moves at 5 meters per second, and we're saying that it's pulling this block, and the coefficient of static friction between the block and the ground is 0.6. What I want to know is how long does it take to move that block. Now, since we're moving at constant speeds, we know right here this is a constant force. Simply put, I have my free body diagram, I define my axis, and we always go back to using Newton's second law. Again, I define the acceleration as 0. So I have my force on the rope is equal and opposite to that spring force. So we know this force on the rope, since I said there's some elasticity to it, is a negative kx equal to my frictional force, which is mu times the normal force. We rearrange my variables, and I know that I can find the distance that rope is going to stretch is going to be about 0.235 meters. Now notice I dropped a negative. Where did that negative go? You know that the angle in between my force is 180 degrees, since they're in opposite directions. So that's going to break out that negative to a positive value. From here, we use simple kinematics, which is our delta x equals v naught t plus 1/2 at squared. Again, we know our acceleration was 0. We know that that truck is pulling the rope for about 0.047 seconds until it actually starts to move. Now, this was a simple example, but it was an indirect question. What makes examples after this harder is, what if we don't have a constant force? Constant force means no constant acceleration. No constant acceleration means we cannot use our kinematic equations. So from here, there are 4 things that I'm going to suggest. Thing number 1, that you read your textbook on this section. Thing number 2, we need to know that conservation of energy does exist. Simply put, for right now, we know that when energy is changing forms, that's going to be our start of conservation of energy. In order to get something to start moving or to stop moving, we know that we're doing work. And work, by definition, means that there's a change in position. It also means there's a velocity and a change in kinetic energy. Lastly, we know if work is done on a spring, that means that material has some elasticity to it, and changing that elastic potential energy requires work. It's a very large circular argument. So here I'm going to suggest that we are going to start by ignoring the actual oscillation. Here I have a picture set up, points A, B, and C. C is that equilibrium position. Point A and point B is if I either compressed or I stretched out that spring. Now we're looking at our maximum positions at part B or at point A. We know that if I compress it as much as I possibly can, the more I compress it, the more force that takes. Same thing with stretching the spring out to point B. If I tried to stretch it further and further and further, I need to increase the amount of force that takes. That being said, we're going right back to Newton's second law. F net equals ma, where my net force is just that force on the spring, my negative kx, as we defined earlier with Hooke's law. That is our mass times acceleration. Now, I rewrote acceleration in terms of velocity and time. Now, the reason I did this, and I'm calling this equation 1, is we know that velocity is a function of displacement, and we know that displacement is a function of time. So we're going to utilize dv dt as our chain rule here. We're going to unwrap dv dt in terms of velocity and displacement per unit time. So we can simplify dv dt and bring it out on the other side with some calculus as v times dv dx. And now I'm over here to continue our conversation. Once I unwrapped with my chain rule, we're going to plug back into what we defined earlier as equation 1. we plug back in, I expanded out my Hooke's law as just the final position minus an initial position. And now I have mv times dv dx. Now here I'm going to integrate both sides, or take the antiderivative. Why would I take an antiderivative just by looking at that? Well, I know if I make a graph of force versus position, if I take the area under that curve, I get a Newton times a meter. A Newton times a meter is a unit of work, and we know the work energy theorem, or the work kinetic energy theorem, is a change in kinetic energy is work. So my units through dimension analysis show that I should take an antiderivative. I'm going to look at both sides separately. The left side is a more difficult antiderivative to take than the right side. To use the left side, I have negative k, which is a constant, which we can pull out. And then we're going to use something that's called the U substitution. U substitution, you're going to learn a little bit of a later date. However, a simple explanation is we take something complex that's hard to integrate, and we're going to make a substitution. Just let u equal that complex term. Then I'm going to let du equal dx so I can integrate. So now I'm left with the antiderivative from my initial position to my final position of u du. When I take that antiderivative, I'm left with my constant, negative k. The antiderivative of u is 1/2 u squared. From my final to my initial position, I plug that in, and on the left side, I have my constant, 1/2 kx final minus 1/2 kx initial. The right side is a much more straightforward antiderivative. We just have mass times velocity with respect to v, mv dv, from my initial to my final velocity. Again, I pull out my constant, take the antiderivative, and it looks very similar to what we just did. So I'm going to be left with mass 1/2 mv squared minus 1/2 m initial squared. And now I collect all my terms. So I have my final terms on one side, my initial terms on the other side. And what does this show? This is a powerful statement that shows two things almost at the same time. One, it shows us that where my velocity is at a max, and velocity will be at max at point C from earlier, where it's oscillating back and forth at that middle position is where that ball is going to be going as fast as it possibly can. It'll also show that at those two endpoints where we started, the velocity will be 0, but my position, final position or initial position on either end, those two positions have the same delta x. Secondly, at those two positions, we have a maximum value of energy, which shows the maximum amount of work means I have the maximum amount of energy. This, by definition, is our stored energy in a spring. We prove here that when my velocity is 0, at either endpoint I have a maximum amount of energy, which means I have a maximum amount of elastic potential energy, or stored energy in a spring, which very simply put is 1/2 kx squared. To check that out with our work energy theorem, if I know work is the integral or the antiderivative of my initial position to my final position of f of x dx, and we know that because as the more force I apply over every small distance, I'm summing up all those forces to get my work all the way across. I substitute in for Newton's second law, mass times acceleration times my change in position. And again, I'm going to utilize that chain rule to find out that work is mass times velocity with respect to a change in velocity. Take the antiderivative, and I'm left with, by definition, work is my change in kinetic energy, 1/2 mv squared final minus 1/2 mv squared initial. So quick check shows the work energy theorem works the second way we did it, and it proves that this conservation of energy theorem does exist. Lastly, for a quick example of a non-constant force, we have a function with respect to x in the I and j hat direction. I know that I can't just use simple work is force times the distance because my force equation depends on this x variable in the I hat direction. So that tells us that depending on where this position is, our force is not constant. I have to use the work energy, not the work energy theorem, sorry. I have to use work, the integral of work as a function of x. So I separate out my I hat and my j hat. So I have f of x dx plus f of y dy, that's my I and my j direction. From my position stated in the problem, I'm going from 2 to 4 and from 3 to 0. Again, take an antiderivative, pull out my constants. Once I do all my math, I find I can add directly the I and the J hat. Again, work is a scalar quantity, so we can add them directly. I know that my work done to move through this position comes out to 44 joules. This does tell us a couple of things. This says that I'm putting work into the system, which shows there's an increase in work. If there's an increase in work, that also shows there's an increase in kinetic energy, which shows that the velocity of the object is getting faster. That's all I have for today. I don't have a bad energy quote for you. I apologize. Please like, comment, or subscribe.